Here's a continuation of group theory. We have some idea of evolving these into a sequence of 1/2 hour lectures, presentations on groups, and maybe rings, fields, vector spaces, and thence to constructibility problems and Galois theory, enough to show that you can't solve a quintic, a fifth degree integer polynomial, with the usual arithmetic operations plus nth root taking. So 24 lectures, it would mimic something of the great courses sequences in math that they have. I don't think it'll ever amount to actually trying to do that, but it's entertainment for me and kind of challenging. So anyway, I want to continue the ideas presented in part one with part two. Part two, the plan would be, and I do this in a rough draft, to take three groups of the same size and to try to fathom when they're the same groups, just labeled differently. So you have modulo 6 under addition, relatively primes, these would be under 18, and there are 6 numbers less than 18 that are relatively prime to 18. 1, 5, 7, etc. 11, 13, 17, I think is it. And the permutations on 1, 2, 3, that's 6 of those jobs. Now, if you had all 3 of these made into a Cayley table, how would you, and you flatten them by making them all in the same notation, namely 1 through 6 and variations on that, how would you tell them apart? The idea, at some point I decided, well, forget trying to do it for a big 6, see if you can do it for 4. So I have 2 groups here, mod 4 under addition, 0, 1, 2, 3, these are extremely easy to make. Modulo 4 under addition, just repeating 0, 1, 2, 3 are the elements, and you make a little table in here, and then you flatten it by making it, instead of 0, you make it 1, 2, 3, 4, doesn't matter how you label it. And then you do another one where you do the Klein group, which is down here, and this one I've already flattened into a bases of 1, 2, 3, 4, those 4 elements. You do, you anticipate Cayley's theorem by translating these 2 groups, mod 4 under addition and Klein 4 under addition. This one I've heard you can get with a isomorphism to Z2, Z2, the integers mod 2, and you can get them into matrix form with these elements. Anyway, so you have these 2, and you figure out that you can represent them in a third way, which flattens them out further into permutations of 1, 2, 3, 4. And you generate these 2 tables, and you notice that they're different in spots. And there you have the challenge of determining when 2 groups of the same order are really just a matter of notation. They're the same group, you just change a notation. When can you look at those 2 groups rendered into permutations on 4 objects and look at the Cayley tables and say, aha, they're the same. And that seems like a very complicated problem. You'd have to do all of the rearrangements of the labels to get them to line up. They should, if it works, have be exactly the same. They don't look the same. Is there a way to get them to look the same by reorganization? Or can you just say, well, they have elements that are not the same? I think that would actually do it. The elements that are not the same from perms 4. And I think that's enough to do it, that you get these 4, 1, 2, 3, 4, and then 2, 1, 3, 4, and 3, 4, 1, 2. Let me see. These 1, 2, 3, 4, 2, 1, 3, 4, 4, 1, 2, 3, and 4, 3, 2, 1. 1, 2. This is shared, so let me try it one more time here. The ones that are circled are the mod Z4 mod 4 under addition, and that's 1, 2, 3, 4, 2, 1, 3, 4, and 4, 1, 2, 3, and 3, 4, 1, 2. Okay, and they're shared. This one is in both the Klein and the other one. The Kleins are 2, 1, 4, 3, 3, 4, 1, 2, and 4, 3, 2, 1 with squares about them. So given that they don't have identical elements, it would seem like the Cayley parallel isomorphisms, the subgroups from S sub 4 that give you Z sub 4 under addition and Klein are different elements, and therefore I think they have to be different. That seems like a good proof. You take that and it anticipates, I think, pretty well Cayley's theorem, that I'm using Cayley's theorem which says that any group is isomorphic to a subgroup if of order your given group factorial, which is huge, right? So this is 4 factorial, which is 24. 4 times 3 is 12, times 2 is 24. And our groups are 4 each, 4 elements. So you need 24, that size group, to find a subgroup within it that will give you Z4 mod 4 under addition and the Klein group. And indeed, you can find those in there and then get an anticipation of Cayley's theorem. My general modus operandi is to try to get examples of what you're talking about first, and then think about it and see if you can do a general proof. So that'd be a perfect instance. We have the specific examples of Klein and mod 4 groups, and we reason it out and say, well, these, if I look at the Cayley tables for these, they're 4 elements and they're organized in certain ways. And that organization could be mirrored, is mirrored in all the permutations of 4 objects, taken 4 at a time. And I look around and figure it out, and indeed I get that Cayley's result for these specific groups of order 4. Then I attempt to figure out how to prove it in a general setting and maybe do some more examples of it. And certainly you could do 6, the 3 groups of order 6 that I mentioned earlier, and it's more, it'd be 6 factorial, which is it 720? You know, so there's 720 rows with 6 columns, and within that you find the 3 groups. And I guess if you find that they don't intersect, or they do, you have they're the same or they're not, question mark. The other thing I wanted to mention, we're at 10 minutes so far, is a general theory that seems to be very helpful for me at any rate, about what group theory is about, and a minor protest that it's taken me a long 20, 30 years to finally get to what group theory is about. And here's what I wrote about this. As it is, we can say, let's see if I can get this here. As it is, we can say the first two are commutative, right? So I have these three. This is commutative, Z6 I've been calling it. The relatively prime under 18, that's commutative. The perms are not. So you can immediately say that the first two are commutative, or abelian, and the last isn't. This is a natural division in the zoology of groups. That's the key phrase. It's a zoology of groups, and you might go to flora and fauna being abelian and non-abelian and play up on that idea a little bit more. Sort of like animals and plants. The animals commute to work, get it, and those are the non-abelian. Are these two abelian groups different? And how would you say that they're different? Maybe all abelian groups are isomorphic. There is only one of a given order. Is that true? And we find out, this is anticipating Solo's theorems, that no, there are abelian groups that are the same size and are different. Same size, different, more than one, different animals. And how do you show that? I think most of Herstein spends a lot of pages saying that's true. Those two are alike, really. It's hidden by the notation, but they are the same thing. Can plants be like animals? So subgroups of non-abelian groups that are abelian. Can these body parts differentiate these non-abelian groups? Body parts would be like the subgroups. And, the organs of a human being, or versus these other animals, they're kind of shared by being a heart, same size, but really different. You would sure think so based on the landscape that plants could be like animals, and indeed within the Cayley's instance of Klein and mod 4, as well as I suspect the mod 6 permutations on 3 elements and relatively prime groups, those exist in a non-abelian, they exist within a non-abelian 6s sub 6 space, which I don't think it's hard to prove. Any s sub 3, s sub n greater than 3, equal to or greater than 3 is non-abelian. So that seems to be the nut of it, and the other big piece that needs to emerge is how do you introduce homomorphisms and isomorphisms naturally in factor groups, and you get to normal groups there, and somehow normal groups will get you to have an arsenal to say whether or not two groups are isomorphic or not, to prove them non-isomorphic, via a lot of numerical analysis of group sizes and group organs, which this has 3 abelian groups of order 2, and it has 1 non-abelian group. And this other thing doesn't have that structure, therefore it's not the same. You'd like, there's one last thing here, a little device. It seems like they must have something equivalent to this somewhere, where you have a group and you have the dimensions and then the number within that dimension. So a group, and it has D1 or dimension 1, dimension 2, dimension 3, and the number in each, and that completely defines a group. You'd like a theorem that says that if you have, I think it's kind of obvious, if you have 2 groups, G1 and G2, and they have this distribution of groups of subgroups of these dimensions, and they don't pair up, then they're not the same group. A isomorphism does not exist between the groups. You'd like, something like that right up front. I think it explains most of Herstein. Just for laughs, here's the contents of Herstein's sections, definition of a group, some examples of groups, and whether or not they're isomorphic or not is a question that you could get right there with examples. Some preliminary lemmas, these are things like the rows in any group have all different elements. The rows in any group have all different elements. Columns have all different elements and all of the elements. And then you prove that, things like the identity is unique and other things. Okay, and then subgroups, Lagrange, the big one, that subgroups have divisor order of the group. Lagrange, Fermat, and Euler. It's curious to see how Fermat and Euler can be proved pretty fast, lightning fast. There's a great course where a guy does it, and there's discrete math, is that what it's called? Discrete mathematics course. He does very fast proofs of these that kind of beg the question whether or not using Lagrange and pumping all this up with the machinery of groups to get at these results is really worth it. It's a nice idea. Counting principle, I think that's the pigeonhole idea. Normal subgroups and quotient groups, homomorphisms, automorphisms, all of these I think generate subgroups and begin to answer the question or give a zoology for groups. Permutation groups definitely gets there because of Cayley's theorem. They refine the notation to make it smaller and smaller and eventually get to alternating groups, I think just the even permutations. Another counting principle, I think that is you have 2 ways to count, and if you use the 2 ways, you can prove results. Silo's theorem, direct products. This direct and finite abelian groups, you do cross products of cyclic groups, give you all the abelian groups. It answers the question, and a result within 14 says how many abelian groups do you get given a order of a group. So I think all of this stuff answers what is the zoology of groups. And then it goes on from there. What's the zoology of rings, vectors, spaces, and fields? And eventually, I think the same kind of idea says when are the sets what are the sets for transcendental numbers, and when is a number in that set, as well as what are a groups that can be solved, a composition of normal groups that means it can be solved, and the lack of a composition of normal groups means it can't be solved. That comes around. All right, so that's about 20 minutes. Call that a wrap.